Hi, everybody. I hope you're doing really well. I hope you're awake and ready for your second to last video on relativity. So, this one should be simpler than what we've talked about. It could be a standalone if you had a friend who wanted to see something or family member. I don't know why they would want to watch one of these videos of mine, but if they were interested in relativity, I don't think they would need to have seen all the previous videos. Now, I will reference them, I'll mention them, but I think you can do fine understanding this concept. It isn't difficult, I think it's just fun. It's kind of interesting. I'll try and make it short and sweet. Last two videos we talked about first time dilation, observers experiencing different velocities, constant motion, relative to the speed of light, not 10 miles an hour versus 12 miles an hour, but big differences so that some percentage of the speed of light would experience reality different in a lot of ways. Time would change, and in those different realities, space would change, specifically length in relative to the direction of motion that that observer is moving. So this topic is called the elsewhere, and I think it's important that we begin from where our conversation left off. This quote has a lot of great significance, something to think about in our current global situation. I'm hoping that you're in a healthy frame of mind. This is always just brilliant advice. This one here from Thich Nhat Hanh, but is one quote about being in the present that is similar to dozens you can find on the internet. And it's just some good common sense advice. I hope you think of this wisdom as we get towards the end of the slideshow, because our topic today will talk quite a bit about the present in terms of our understanding of Einstein's theory of relativity. Like I said earlier, all sorts of things change, including time, concepts of space, as well as our definition and understanding of the present. So we're talking about the elsewhere. First, let's review this concept about length contraction. We could have two events here. In a certain, there are certain classification, category of events for which different observers would experience them so differently, the observers would argue about what happened first. We on Earth might see these two space shuttles pass overhead and say that when the left ends lined up, the right ends lined up too. So there's two different events. The left end's lining up and the right end's lining up, and in fact, they happened at the same time. We thought they were simultaneous. Another observer would say, no, the left end's lined up first. So they weren't simultaneous. And a third observer might say, oh, no, the right one's lined up first. So they won't even agree on the sequence of events. They would argue about the order that they took place. And they would all be correct. All three observers would be experiencing and describing their reality accurately. They would all be very reasonable because all three of those realities are valid. They're just different. Okay, so those were the fun ideas from our last conversation. Sorry that my face is in the way of those words there. I can't really change this, and I won't be recording this video, so it looks like that might be happening this time. I don't think it did a lot in previous videos. We want to review the concept, the definition of the word event, anything that has a specific time and place. Pretty similar to a common sense, everyday definition of the term event. But we're going to have some definitions that are very specific to the theory of relativity today. So we're going to start off with our vocabulary from last time. Now here's an example as we introduce our new topic of the elsewhere. Let's talk about your birth. There's an event, had a time and a place. Now, depending on how old you are, there's a different length of time that has transpired between when you were born and when you're watching this video. And it'll be a little bit different for all of us. Okay, now different observers would experience that time amount differently. How about cause and effect? So here's the first question, and then I'll stop the video and let you answer. I want you to actually write down what you think. Does your birth have to take place before you watch this video or not? Is it in fact impossible to watch the video now if you haven't already been born at some point in the past? Take a couple minutes right now. Okay, of course you have to be born before you can watch my video. But as I referenced, as I mentioned already from our last conversations, there are situations, some events where people will reasonably argue about which thing happened first. Your birth and the watching of this video is not one of those events, one of those situations. We would all agree that you were born first. But there is a group of events, a category, in which case people would argue about what the sequence is, what happened first, what happened second. Those events occurred in the elsewhere, the topic for today's conversation. So here's the definition. As we begin right away, I want to tell you here's what the definition is, and then I'll give you some examples to explain it, and that'll be the whole video. So there are a class of events that occurred really far apart in space, but in a very short amount of time. So they were separated by grand, vast distances, but only a small amount of time. Okay, those events occur in something we call the elsewhere, that's outside of our normal understanding of time. And then different observers would argue about, did they happen simultaneously? Did the event A happen first? Did event B happen first? So they would even debate the sequence, the time order of those events. Okay. For this category of events, there is no cause and effect. You can't say that event A had anything to do with event B. You can't say event B was a result of any part of event A. They're just so separate from each other. There's no relationship, no cause and effect. Unlike the twin paradox, there is no paradox. There's no contradiction. It just is strange that there are different realities, so that one observer might say event A happened second instead of first. That's unfamiliar to us here on Earth, but there is no paradox. For example, with the twin paradox, it seems to violate this principle of relativity that says, well, we all have the right to claim that we're stationary. It just looks like other things are whizzing past us. The ancients, I guess during the Middle Ages in Western culture, thought that the sun rose in the east and set in the west, and the earth was still, and it's reasonable. It kind of looks that way. So even if you're in a rocket ship, you turn it on, there's this loud noise, and it could just look like space is moving past you. Oh, look, here's that planet going past us. And that's reasonable, in which case I might think, oh, the people on Earth, we flew past it in a rocket ship. As we turn on a rocket ship and Earth flies past us, they're moving at a fraction of the speed of light, so their clocks must be running slower, and they might look up at our spaceship whizzing across in the sky and say, oh, they're moving at a fraction of speed of light, so their clocks must be running slower. Those realities are both fair and true, but in the case of the spaceship, the twins that separate, one becomes an astronaut, takes off, turns around, comes back. That is no longer the case, that you could say they both feel that the other brother should be older. In fact, the astronaut would be older, and there's only one right answer there. The observer, the twin who stayed on Earth, would be younger. I said that backwards. The one who stayed on Earth would be older, and the astronaut would be younger. And there is only one answer there. And we talked about why. But so there's no contradiction. It doesn't actually break any laws. There's a reason for that. And similarly now with these events in the elsewhere, they follow all these principles that we've talked about. They follow all the rules of physics, just like the definition of the theory of relativity says. So there's no contradiction anywhere. And of course, they cannot have any influence on each other. They're trapped out of our concept of time, and they have no way to connect with each other because they are separated from each other's present. Their presence, the present of this event and the present of this event, are completely disconnected. There's no way for them to communicate, so they can't influence each other. All right, no cause and effect, no contradiction of reality, no influence. Let's go back to this concept of you being born and then sometime later watching this video. There's a distance from wherever you were when you were born. That was an event. So there was a time and a place. And then you're now watching this video somewhere in your living room, your bedroom, I don't know where. All right? Not in my classroom, sadly. So there's a time and there's a place, and that's a different event. The distance between those two is pretty small. Remember I said that the definition of events that fall into the category of being part of the elsewhere had to be really separated by big distances in space and only small differences in time. We don't have a huge distance and separation in space here. What we have is a small separation of space. Even if it's 1,000 miles, you were born in Siberia or Antarctica, someplace that seems far from Wyoming, and the vast expanse of space, it's not very far, a few thousand miles, right? And those 16 years, 17 years, for me, 52 years is a pretty long period of time in comparison, okay? Could light have possibly left the event of your birth and then traveled here? Yeah, light can go all the way around the Earth in less than 1 second. Light can go all the way from here to the moon in 1 second. That's 250,000 miles. They'd have no problem. A light beam, a radio signal, a radio transmission, a cell phone call would have no problem going from wherever it is you were born on planet Earth to wherever you are right now. So, light could easily make that journey millions of times between when you were born and now. So that doesn't fit into this classification, this category we call the elsewhere. All observers would agree. You were born first, then you watch the video. Okay, let's talk about a different example. Andromeda Galaxy is our nearest neighbor. You probably don't write this down when you apply for jobs and stuff, but your address is actually blah, 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 Lander, Colorado, United States of America, United States, North America, right? Planet Earth, and etc. Our solar system around the sun, and eventually the Milky Way galaxy. That's our galaxy. And we think in the visible part of the universe that we can see there are something like 200 billion galaxies just in the visible universe that's nearby us. And the very nearest of those galaxies is the Andromeda Galaxy. It's the farthest thing you can see with your eye. If you use your eyes and nothing else, your naked eye, unaided by a telescope or binoculars, and you know where to look, there's a faint, dim smudge of light in the Andromeda Galaxy constellation, and that is the Andromeda Galaxy. That light is 2 million light years away. That's a distance, meaning it takes 2 million years for that light to come and hit your eyeball. So, like other stars in the night sky, when you're looking at it, you're not seeing what it looks like now. You're seeing what that galaxy looked like 2 million years ago. It could have blown up 1,000 years ago and not exist anymore. It's an image, it's light, finally arriving at Earth and going right through the pupil of your eye and hitting the retina on the back of your eyeball and triggering these photoreceptor cells that send a signal to your brain. And you say, oh, a blurry, dim smudge of light. Right? That light traveled for 2 million years. Who knows what's going on with the Andromeda Galaxy now? Okay. So let's say that while there's two events. One was a student in my class who was born about 16 years ago, and at that very moment, we think, with respect to our sense of time here on Earth, that very moment in the Andromeda Galaxy, there was some event that happened there. So my student's about 16 years old. About 16 years ago, something happened on Andromeda. But in that time, light couldn't have traveled very far away from Andromeda. If a signal at the moment of that event in Andromeda, a signal was sent to Earth at the fastest speed that exists, the speed of light. Let's say they sent a radio signal. They made a cell phone call. Hey, this cool event happened. That light has only been able to travel the speed light can go during 16 years of time, and it needs to go for 2 million years. It's barely gone anywhere. So now we have an event that's separated by two events, separated by really big space of time, a very big distance in space, and a very small amount of time. 16 years isn't enough time for that light beam to get here. There can be no cause and effect relationship between those events. The student in my class can't say, oh, I think, given all that happened in the Andromeda Galaxy 16 years ago, I'm going to wear these red socks today, right? There's no cause and effect. Let me go back here because maybe I need to ask you that question here a little bit. There's no cause and effect because that student has no idea that this event took place in the Andromeda Galaxy. We on Earth won't know about it. We won't receive that phone call for another 2 million years. If the distance is exactly 2 million years, it's 2 million years minus 16 years, but it's still about 2 million years, right? We're going to have to wait forever, seemingly, before we get that call. We have no idea the event occurred. We cannot know the event occurred. Even light can't get here yet from the time of that event. So we have no information about it. There's no way it could affect this kid's choice as he was dressing in the morning. Okay, there's no cause and effect relationship because we don't know about it. There's no contradiction of reality, right? Both our reality, our sense of time here, the reality in Andromeda, this different set of motion in the universe, they're both valid. There's no laws of physics being broken. There are no paradoxes. There's just no information and no ability to influence each other because they're too far apart. Even light can't travel between these two events. This is another example of two events that have occurred in what we call the elsewhere. Now, there's some people who would think that the event that happened in Andromeda was first. There's some people who would think that those two events happened simultaneously. There are some observers in the universe who might think, rightfully so, that the event on Earth happened first, and they're all valid. None of those is more correct than the other. The theory, the definition of relativity is those are all equally correct perspectives. Okay, but we would argue we'd have different observers having different experiences with their different realities, and they might disagree on the sequence of what happened first. That's the case about all events that occur or take place in the elsewhere, which actually isn't a place. It's a reality that's out of sync with the present time. All right. Here's an example I think you'll understand really well, and this is probably all you need. Now that I've warmed you up, this is all you need probably to explain this concept of the elsewhere to some friend of yours who's interested in the theory of relativity. Okay. 2012, we sent this U.S. rover to Mars, landed it on Mars' surface. Now, we picked a time when Mars and the Earth, they're both orbiting around the sun. They both happen to be right around the same spot in orbit around the sun. They're right near each other, Mars and Earth. Sometimes one planet is on one side of the sun, another planet's on the other side of the sun. The distance is huge. So we picked a really good time when they were relatively near by each other. At that moment, when we landed Curiosity rover on Mars, Mars was 14 light minutes from Earth. There's Curiosity, cute little guy. So we have this 14-minute delay. When we send a radio signal to the rover, it takes 14 minutes to get there. When we sent Neil Armstrong and Buzz Aldrin to the moon in Apollo 9, I don't know when they landed on the moon, there was a 2-second delay. So it was a hard thing for the people in mission control to communicate with the astronauts. They'd have to wait 2 seconds for it to arrive. Astronauts would think, astronauts would respond. There'd be another 2-second delay before the people in mission control get an answer. With Mars, there was 14 minutes time for the transmission of a radio signal from mission control to the rover. Imagine now there's a problem. Our engineers and mission control, with the camera mounted on board the rover, they see, oh my gosh, there's a landslide. Look at that huge boulder. That gully's heading right for the Mars rover. And let's say that the rover had been there for a while, and they'd looked at the cameras. Scientists didn't know what to do, and so they were calculating what they could. They were trying to process what information they had at this point. And they had already calculated, and the scenery in the background has a hill there, and they'd calculated, looking at shadows, that's 8,000 feet tall or something. Well, they all of a sudden see this landslide, and there's a boulder right at the bottom of that gully is the Curiosity rover, and they calculate quickly. We think we have about 5 minutes until that boulder crushes the rover. Can they send a warning? Can they quickly send off a message, give instructions for the rover to go hide behind that big cliff or that big rock so it won't get crushed? Of course they can. They just go, whatever they do, send off their message. Will that help? Why? I'm going to pause for a moment. I want you to write in an answer. All right, welcome back. The message will take 14 minutes to get there. So if there's a warning, in 5 minutes the boulder will crush you, there's not enough time for the Mars rover to receive instructions and then move behind the rock for protection or shelter. Right? There's nothing the mission control engineers can do to influence the outcome. All they can do is sit there and watch as slowly. There's this time delay, and the cameras show what happens with that boulder. Okay, they can't help. Now, if that mountain were bigger, the boulder were rolling slower. Gravity's weaker on Mars. Maybe it would roll slower. If they thought they had 15 minutes or 20 minutes, they could have said, here are the instructions, quick, move to, and had the rover pulled in behind that cliff or that big boulder or that big rock that might protect it. But they only had 5 minutes. The 14-minute delay meant there was no chance that they could do anything to help. They had no influence over the rover. Okay. 14-minute delay, frustration. Our present was out of sync with the present on Mars. Okay, now how about this? Let's take the same scenario. Okay, got a boulder. Let's say it rolls down the hill and crushes one of the rovers, and that happened 5 minutes ago. There are hundreds of people who have worked on this thing. It was built at the Jet Propulsion Laboratory in Pasadena, California. So JPL had hundreds of people there. They probably spent 15 years proposing and developing and tinkering with the idea, and eventually designing and making mock-ups and testing it and improving it, revising it. 15 years. NASA probably spent $150 million, I don't know, to build that rover, pay for it to be added as a payload to a shuttle, pay for the extra fuel, get it launched into space, and get it landed, right? They were probably at Lockheed Martin, hundreds of people who worked on that process in one way or another. There were probably millions of citizens who were at their hopes up and were watching this thing, and really little kids were excited, right? It happened 5 minutes ago. The thing got crushed. Does anybody care? Are people upset, disappointed, defeated? Has funding been cut to NASA? Nobody knows about it yet, right? Nobody's upset. It doesn't exist in our present. The thing was crushed. It's just a bunch of recycled scrap metal now. It's a bunch of litter, trash on the surface of Mars, and nobody knows. It doesn't have any effect or influence on us right now in our present because it doesn't exist in our present. That information doesn't exist for us yet. I find this so interesting. I don't know why. I find it really fun. Okay. Now, they have no cause and effect on each other at all, these two events. Right? The event of our present and the fact that 5 minutes ago the rover got crushed. I had here in green why. I wanted you to write that down. I've already answered it, so I'm going to just move on. Here's my little diagram there. There's a 14 minutes ahead from the present, 14 minutes behind from the present. There's this 28-minute window in which we have time disjointed between the present moment on the surface of the Earth. Let's say that Mars was now 14 light minutes away from us, and then the reality on the surface of Mars. We've got 28-minute window, 14 minutes in the past plus 14 minutes in the future. Okay, so these events are not tied to our present. Something going on the surface of Mars in the last 14 minutes or in the next 14 minutes, it's got nothing to do with our present. It's actually never going to be part of our present. They only exist in the future, and then they disappear. And all of a sudden, boop, they appear. They suddenly, all of a sudden, just appear magically in our past, but they skipped over our present. So we need, first of all, before we conclude this lecture, to have just a definition of what do we mean by past and present, right? We need some relativistic definitions. Now, we could maybe guess how a historian would define the past. Let's start there. What is the definition of the past? I want you to take a moment and fill that in. If you want an extra challenge, I want you to guess, before I give you this answer, guess, what do you think Einstein would say when we ask him to define the past? What would be a good relativistic definition of the past? So answer either one of those two questions. All right. The relativistic definition for the past is all those events that can influence our present. We learned some powerful things about using gas warfare in World War I, about technology and ethics and nuclear warfare in World War II, and lots of other stuff, right? Racism, totalitarianism, dictatorships. Could those events have influenced people's political opinions today? Sure. Could they affect maybe how someone's going to vote in the election next November? Yes. There's been plenty of time for light to travel from, Germany or whatever to the United States in the last 60 years, etc. There's been lots of time, last 100 years since World War I. So we're aware of those events. They exist in our past, and with that knowledge, we might have a different opinion than we would have otherwise. We might have different political views. They can influence us. If they didn't exist for us, they could have no influence on us, like maybe what's happening right now, this moment on Mars or in the Andromeda Galaxy. I won't know about it for a while, so it's not going to affect my opinion right now, right? But things that are already in the past can influence the present. So how do you suppose Einstein would define the future? Let's take a moment to think about that. I won't have you write it down. What would be a good relativistic definition of the future? The future is all events which we in the present can influence. So I become a teacher and decide education is really important. And I learn a bunch of things about kids' work ethics and discipline and follow through and whatever. And then I have a child. Is it possible that all this stuff in my present would influence my parenting style and philosophy? Maybe, right? But by the time I have my child start parenting, right, this stuff will be a part of my child's and my past. And certainly I will have knowledge about the experiences I had as teaching, right? The past can influence me. And today, our present is going to be eventually the past. We are living the future's past. The definition of the future in terms of the theory of relativity is all events which can influence it. Okay. Definition of the future. All all the future is includes all events which we in the present have influence over. We can't influence the past. What I'm thinking, what color socks I wear today, isn't going to affect the outcome of World War II, but it might have an impact on my unborn child, something in the future. Okay. So, with this example we had about Mars, we have these 28 minutes that are permanently disconnected from our present. They're separated by big distances in space and small amounts of time. Just like our example on the Andromeda Galaxy, this weird gap where we're out of, there's this time gap, like the lag time of 4 seconds when mission control would ask a question to astronauts on the moon and have to wait for a response, right? That awkward gap is what is referred to as the elsewhere. Now, they're not lost forever. The thing that's weird, I've already said it, is they're just disconnected from our present. They're in the elsewhere. It's weird. We can't connect with them. It's present happening there on Mars. It's present happening here. We got all this fancy technology and radios, and we can't connect. We have no ability to exchange information. We have no knowledge of them. We have no influence. They exist in our future. Oh no, there's a rock coming. I can see it on the camera. And then all of a sudden, boom, they exist in our past. All of a sudden. But they, in the meantime, hopped right over our present. So they went straight from the future to the past, like a lot of things we experience in our life do. But unlike anything we've ever experienced in our lives, it skipped today. It just hopped over our present and boop, appeared in our past. I don't know why. I really like that. That's the elsewhere. I hope you liked it too. Easy, no math. In 2020, I made this series of videos for my zombie apocalypse students. Maybe other people will watch it in the future, but I don't know about that right now. And in that series, I have one left. We'll talk about black holes and general relativity as our last topic. Hope you have a great day.